The third type of thermodynamic processes are isothermal. The heat or volume of a system is then changed very slowly so that the other properties can adjust while the temperature essentially stays constant. An isothermal process is kind of like an isobaric process in that if you add heat, the volume will expand, so the system will do work. But for isothermal processes, you can't use that simple W equals P delta V equation because the pressure does change. Instead, you need to take the integral of the pressure with respect to volume. This way, you're still calculating work, but you're taking the changes in pressure into account too. Another difference between isobaric and isothermal processes is that since temperature is held constant in isothermal processes, the internal energy of the ideal gas can't change. And the first law of thermodynamics says that heat minus work is equal to the change in the internal energy of the system, in this case, 0. So the work done by the system will be equal to the amount of heat added and vice versa. Finally, there are adiabatic processes where no heat is allowed to flow in or out of the system, but the gas can expand or be compressed. Again, the equation for the first law of thermodynamics helps us out here. Q is 0 because the heat of the system isn't changing, but the internal energy of the gas can change, so the system can do work or have work done on it. In fact, the change in the internal energy of the gas will be exactly equal to the negative of the work. But this is all just the first law of thermodynamics. There's also the second law, which says that heat will spontaneously flow from something hotter to something colder, but it won't flow from something colder to something hotter. And that's because of this thing called entropy. Entropy is often described as the inherent disorder of a system. The more disordered the system, the higher its entropy. So a gas, for example, with all its molecules randomly bouncing around, has a higher entropy than a solid with its molecules neatly arranged. And a more general way to state the second law of thermodynamics is that in real life, entropy can only increase overall. That doesn't mean that entropy can never decrease in certain situations. But if the entropy in a system decreases, that means the entropy of the environment around the system must increase enough to compensate and then some, so that there's an overall increase in the entropy of the universe. Say you put water in your freezer to make ice, for example. The entropy of the water goes down as it freezes. But meanwhile, your freezer is putting out heat as it works to keep itself cold inside. And the heat from your freezer is increasing the entropy of your kitchen more than the entropy of the ice is decreasing. So overall, there's an increase in the entropy of the universe. Now, entropy's tendency to increase has to do with probability. To see what I mean, picture a shattered ceramic mug. There are molecules that make up that mug, and there are lots and lots of ways that those molecules can be arranged in space, and all of them are equally likely. But still, there are lots of possible arrangements of those molecules where they could make up a shattered cup, a set of pieces with a higher entropy. The cup can be shattered into pieces, 300 pieces, with the pieces far apart or very close together. And every way the cup can shatter is another possible way for the molecules inside the pieces to be arranged. On the other hand, it's very likely that a cup that's whole will break when you drop it. So the process that leads to an increase in entropy has a much higher probability of happening. And in thermodynamics, entropy is related to heat flow because when heat flows between systems, their entropy increases. But when their temperatures become equal, that need to organization is gone, so the systems have a higher entropy, which is also why this little bird keeps bopping up and down. When the heat flows out of it, the gas condenses and it dunks into the water.